Imagine a bustling kitchen where each dish is a masterpiece crafted with precision step by step, following a recipe. In the world of computing, this recipe analogy helps us to understand machine language instructions, the fundamental recipes that the CPU follows to perform tasks. Written in binary, these instructions guide the computer in its operations, ensuring seamless execution of even the most complex tasks. Let's dive into this fascinating process. Every machine instruction is like a line in a recipe, composed of first one, opcode, the action to be performed, much like stir, bake, or chop in a chopping guide. In binary, these are unique integers. Example, 0 for add, 1 for compare. The number of possible operations depends on the number of bits used in the opcode. Second one, address fields. The ingredients or locations involved in the operation. If your kitchen has 256 ingredients, that's memory cells. Each address field needs 8 bits to locate any ingredient. For instance, to add ingredients X and Y, the add operation fetches the values from their respective addresses and combines them. A comparison operation might test whether an ingredient, example stored in cell X, is negative. Let's imagine you are following a recipe. The program counter. This is your bookmark, keeping track of which steps in the recipe you are on. After completing a step, you move the bookmark to the next, ensuring you don't lose your place. Similarly, the program counter holds the address of the next instruction and increments after each fetch, keeping the CPU progressing in sequence. Next, the instruction register. Think of this as the step you are actively reading. You fetch the bookmarked instruction and copy it into your mind to follow. Similarly, the instruction register holds the fetched machine instruction, ready for the CPU to decode and execute. The instruction decoder. This is your ability to interpret the recipe. You read chop onions and know you need a knife and a cutting board. Similarly, the decoder needs the opcode from the instruction register, understand what operation is required, and signals the CPU components, like the ALU or memory, to perform the task. So, together these three components ensure the CPU fetches, understands, and executes instruction in perfect harmony. Here's how this culinary computation unfolds. The program counter PC provides the address of the next instruction to be fetched from memory. The fetched instruction is stored in the instruction register. The instruction decoder reads the opcode and activates the appropriate control signals, triggering components like the ALU or memory to execute the operation. For example, let's decode a load operation. The opcode, example 001, signals the instruction decoder to act the load circuitry. The instruction register sends the address field to the memory address register. Data is fetched from memory into the memory data register and then moved into an ALU register for further processing. Picture a conductor leading an orchestra, where each gesture corresponds to a specific section playing its part. In a CPU, the instruction decoder acts similarly. It takes binary opcodes, example 000-001 as input. Each opcode maps to a unique operation. For instance, let's 000 to be add, 001 to be load, 010 to be jump, 111 to be halt. When an opcode is decoded, the corresponding control line is activated. Dedicated circuitry for the operation springs into action. For example, an add operation 000 activates the add circuitry, fetches two operands into the ALU registers, computes the results, and stores it in the destination register. The entire process follows a structured flow, much like cooking step by step. Fetch. The program counter fetches the next instruction from memory. Decode. The decoder interprets the opcode and address fields. Execute. The CPU performs the operation, whether it's a calculation, data transfer, or comparison. This cycle repeats continuously, enabling the CPU to execute programs with incredible speed and accuracy. Every CPU operation is a beautifully choreographed sequence, turning binary instructions into actions. From fetching the next step in a recipe, program counter, to understanding its meaning, instruction register and decoder. The CPU ensures seamless execution. Just as a chef transforms simple ingredients into a delicious meal, the CPU transforms binary code into tangible results, powering the digital world we rely on.